Bismillahirrahmanirrahim. Here is the outline for today's lecture. We will start with the basics of the Laplace transform and how to use Laplace transform for circuit analysis. Then we will check how to find Laplace transform of the given signal waveforms. The properties of the Laplace transform including linearity property, integration, differentiation and the translation property would also be covered in today's lecture. Towards the end of the lecture, there will be few questions for you to think about and gauge your understanding about what we have covered in today's lecture. Let's start with the Laplace transform for circuit analysis. What is a transform? A transform means to change the form of the data without altering its meaning. Let's say we have a numerical value, let's say 15. So 15 can be written in the decimal format as 15. The same information, the numerical data of 15 can be written in the binary form as of tetra 1. So the main information is same, numerical data is 15 and it is written in the decimal format as 15 and it is written in the binary format as tetra 1. And in certain cases we might be finding it easier to deal with the decimal data, and in certain format we might be finding it easier to deal with the binary data. Same is the case with the transformations used in the engineering. Before covering the Laplace transform, we have covered the phasor representation of a sinusoid, where we converted a sinusoid into a phasor domain. And in this lecture we are going to deal with the Laplace transform, and the Laplace transform transforms a time domain signal into a complex frequency domain signal f of s. Symbolically we represent the Laplace transform by Laplace. This fancy L is used to represent Laplace. So Laplace of a time domain function over here is represented by f of t. Laplace transform of a time domain function f of t is represented by capital F of s. Letter used is same, whatever the letter we are using over here, same letter would be used to represent its transform but with a capital letter. And t represents the time domain function, whereas the s represents the transform in s domain. What is s? S is equal to sigma plus j omega. And s is a complex frequency having units of radian per second. Units of s are inverse of the time. So the difference between the phasor domain and the Laplace domain is, in case of phasor domain, our input signal was only a sinusoid signal. Only the sinusoid signal can be converted into phasor domain. Here the input signal needs to be a time domain signal. It can be a sinusoid, it can be an exponential function, it can be a step function, or it can be any other time domain function. A signal can be represented by a waveform or a transform. Time domain signal, we will be calling it a waveform, and the S domain function would be known as the transform. How will we be using the Laplace transform for circuit analysis? This flowchart over here represents the procedure. We will be given a linear circuit, then we will write the differential equation describing that linear circuit. After writing the differential equation, we will take the Laplace transform of the differential equation. Once we have taken the Laplace transform of the differential equation, our differential equation would have been converted into an algebraic equation. And once our equation is an algebraic equation, we will be using algebraic techniques to solve that algebraic equation, and then we will find our response transform. Let's say if we need to calculate voltage, we will be calculating voltage in S domain, complex frequency domain, and once we have calculated our voltage or the current in complex frequency S domain, then we will take the inverse Laplace to convert the S domain function or the transform to a time domain function. So this inverse Laplace would convert an S domain function into a time domain function. So our result would be over here. So this procedure, this line is representing the procedure which we will be adopting in case of this chapter means the analysis of the circuit using the Laplace transform. How to calculate the Laplace transform of a function? This is the formula or the equation which is used to calculate the Laplace transform of a function. F of s represents the transform. So, the transform of f of t can be calculated using this formula, which is integration from 0 minus to infinity. What is 0 minus? 0 minus means just before 0. In mathematics, most of the time this lower limit is taken as 0. In electrical engineering, the lower limit is known as is taken as 0 minus. Effectively 0 and 0 minus are same, but why we have used it 0 minus over here, it would be explained soon. Function f of t, which is the time domain function, multiplied by a decaying exponential function e raised to power minus st and integrated over a limit from 0 minus to infinity. This f of s is known as the transform in s domain, and this f of t is the function in time domain. There are two conditions for the convergence of this integral, because integration limits are from 0 minus to infinity. So the the conditions for the convergence of this integral are, there are two conditions. First condition is f of t is a piecewise continuous function. What is a piecewise continuous function? Piecewise continuous function means that the function has finite number of discontinuities in the finite interval. It means finite number of discontinuities in the function are possible, but if there are many discontinuities in the function within a finite interval, it means the integral may result in an infinite value, and infinite value would be of no use for us. So, because in electrical engineering usually the switch closes or opens at time t is equal to 0, therefore in order to include that discontinuity occurring at t is equal to 0, we have used the lower limit as 0 minus, so that the number of discontinuities in the function f of t within a finite interval are finite. An example of piecewise continuous function is, let's say we have a light, and light, like turning on and off a light within like 1 second is finite. If it is finite, it means the Laplace transform of that function is possible. But if the light is flickering like millions time in 1 second or in finite amount of time, it means there are infinite number of discontinuities, or there are huge number of discontinuities in the function, therefore the Laplace transform of that function is not possible. Second condition for the convergence is f of t is of exponential order. What does this thing means? This thing means that the function f of t must not be rising wildly. F of t, magnitude of f of t must be less than an exponential function k into e raised to power bt. K is a constant, b is a constant. This is basically representing an exponentially increasing function. So the magnitude of the function must be less than an exponentially increasing function. It means the rise of the function f of t must not be very high or infinite. Let's say we have a function e raised to power t square. The rise of this function is very quick, therefore this f of t is not of exponential order, therefore the integral might result in an infinite value and we might not be able to calculate the Laplace transform of the function. Almost all the signals encountering in electrical engineering or in engineering application meet these conditions, these two conditions, that f of t is a piecewise continuous function and f of t is of exponential order. Now, coming to the units of f of t. In electrical engineering, f of t would be usually a voltage signal or a current signal. So, the units of voltage are volts and the units of current are ampere. It means units of f of t in most of the cases in electrical engineering are going to be volts or amperes. When we transform the signal from time domain to complex frequency S domain, or we take the Laplace transform, because we multiply f of t by e raised to power minus st and dt and integrate it. So what are the units of e raised to power minus st? We have already discussed that the units of s are inverse of time. St, units of st would be unitless because s has units inverse of time, time has units seconds. So st is going to be a unitless quantity. So e raised to power minus st is going to be a unitless quantity. What about dt? dt is a very small interval of time. So it is going to have units second. So f of t, which has units voltage or volts or current, multiplied by t, going to result in volts second. It means the units of f of s are going to be volts seconds or ampere seconds. Let's calculate the Laplace transform of the few basic functions. Please keep it in mind that the number of functions used in electrical engineering are not going to be very high, and we must remember the Laplace transform of these basic functions so that we can use the Laplace transform of these basic functions. We need to solve like bigger or complex equations. So f of t is a unit step function. F of t is represented by u of t, and we are interested in calculating the Laplace transform of this function. So Laplace transform, which would be represented by f of s, we know that f of s would be equal to, this is the formula, integration from 0 minus to infinity f of t into e raised to power minus st dt. So I can insert the value of f of t over here. So this is going to be 0 minus to infinity u of t, and we know that what is u of t? U of t is a unit step function. Value of the unit step function is either going to be 1 or 0. Value is 1 for t greater than equal to 0, and value is 0 otherwise. So we can write it u of t equal to 1 in the range from 0 to infinity. So f of s would be equal to, from 0 to infinity, value is 1, therefore 1 over here into e raised to power minus st dt. What is the integration of e raised to power minus st? E raised to power minus st, integration of e raised to power minus st is e raised to power minus st, and we need to multiply and divide by e raised to power minus s. Therefore, when we insert or when we substitute the limits, f of s results in e raised to power minus infinity, which is 0, minus e raised to power minus 1, e raised to power minus 0, which is 1, over minus s, which is going to be plus s over here. So 1 over s, very common function for which we need to use or we need to calculate the Laplace transform is the unit step function, and I would encourage you all to remember this Laplace transform, that the Laplace transform of a unit step function is 1 over s. Next is the function for which we want to calculate the Laplace transform is an exponential function e raised to power minus alpha t into u of t. This is the product of two functions, e raised to power minus alpha t into u of t. So the Laplace transform, where the formula to use to calculate the Laplace transform is this formula, and I'll be inserting the value of f of t in this function. That would be f of s equal to integration limits from 0 to 0 minus to infinity e raised to power minus alpha t u of t e raised to power minus st dt. F of s would be equal to, because this u of t we already know that the value of unit step function is 1 from 0 to infinity, and for other values value of u of t would be 0, and when u of t is 0 it means everything, the product of all the functions would be 0. Therefore we are changing the limit from 0 minus to 0. Effectively 0 minus and 0 are same anyway, so e raised to power minus st into e raised to power minus alpha t. So we can take minus t common, e raised to power minus t into alpha plus s into dt. Minus t can be taken common, and the rest of the thing in the power would be alpha plus s into dt. When we need to integrate e raised to power something t, it means the derivative of this thing must be existing over here. So the derivative of this thing would be minus alpha plus s. So we need to multiply and divide by minus alpha plus s. So it would be minus division 1 minus alpha plus s and e raised to power minus t into alpha plus s multiplied by minus alpha plus s into dt. Because we have the derivative of the power existing over here, therefore the integral of e raised to power minus t into alpha plus s is going to be e raised to power minus t into alpha plus s. So f of s would be equal to e raised to power minus t into alpha plus s divided by minus alpha plus s. Substituting limits, when we substitute the upper limit, it is going to be e raised to power minus 0, which is going to be e raised to power minus infinity, which is going to be 0. So f of s is going to be e raised to power minus infinity, which results in 0. So I'm not okay, 0 minus the lower limit. This negative sign over here and this negative sign over here is going to make it positive. So e raised to power 0, which is going to be 1 over alpha plus s. So result is f of s is equal to 1 over s plus alpha. This is one of the very important property which we will be discussing next, that when we calculate the Laplace transform of the function u of t, we got Laplace transform was equal to 1 over s. When we multiplied the u of t, it means we multiplied the function u of t by e raised to power minus alpha t. What is the result? This s in the denominator over here is basically shifted by the same amount s plus alpha, which amount with which the time domain function u of t was multiplied by an exponential function e raised to power minus alpha t. So this minus alpha is going to shift this s by an amount s plus alpha. This property is known as S domain shifting property, but we will discuss it in detail in coming slides. Third function for which we are going to calculate the Laplace transform is the impulse function. What is an impulse function? Impulse function has an amplitude 1 at t is equal to 0 and the amplitude is 0 otherwise. This is the sketch of the Laplace of the impulse function. Here I have sketched the axis, impulse, amplitude 1 at t is equal to 0. This is t is equal to infinity and this is t is equal to minus infinity. So the amplitude is 0 starting from minus infinity to 0 minus and plus 0 plus to plus infinity. Amplitude is 0 and amplitude is 1 when t is equal to 1. When we calculate the Laplace transform of this function, we need to substitute f of t in this formula. So our f of s would be integration from 0 minus to infinity of f of t. F of t is impulse into e raised to power minus st dt. The value of the impulse function is 0 when the time is other than 0. It means this value of impulse function is 1 at t is equal to 0 only. It means we can write this function as integration limits from 0 minus to 0 plus. Only in this range the value of the impulse function is 1, and in all other ranges value of the impulse function is 0, therefore e raised to power minus st dt. So we have basically divided the limits in 3 different regions. One is this region from minus infinity to plus 0. Another region was not in 3, rather in 2 different regions. So one was 0 plus to infinity. And in this region from 0 plus to infinity, because the amplitude of the impulse function is 0, therefore the product of impulse of t into e raised to power minus st is going to be 0. So this is written like this. So f of s would be equal to integration limit for this integral is from 0 minus to 0 plus. 0 minus to 0 plus is effectively a single point. This is not a range. The lower limit and upper limit are same. It means the value of t is going to be 0 over here. So when we insert t is equal to 0, it would result in 1. So this is going to be 1. We have not integrated 1 over this range because this range 0 minus to 0 plus is effectively a single point. Therefore, we just inserted the value of t is equal to 0 over here, and this is the result. So Laplace transform of the impulse function is 1. How do we need to calculate the inverse Laplace transform? Symbolically, we represent the inverse Laplace transform by Laplace inverse, this fancy L, Laplace inverse of f of s, and it result in the time domain function f of t. The formula used to calculate inverse Laplace transform is this, a complex formula, 1 over 2 pi j integration limit from alpha minus j infinity to alpha plus j infinity and integration of f of s multiplied by e raised to power st ds. But don't worry about this complex formula because we are not going to use this complex formula to calculate inverse Laplace transform. Rather, we are going to rely on our basic knowledge of Laplace transform while calculating the inverse Laplace transform, because we have only like finite number of functions, very few functions, maybe like no more than 10 functions. 3 of them we have already covered. Which 3 of them? We have calculated the Laplace transform of a unit step function, which we checked in previous slide that it was equal to 1 over s. So whenever we need to calculate the inverse Laplace transform of 1 over s, we'll directly rely on our knowledge, and we will say that the inverse Laplace of 1 over s would be unit step function. Secondly, we calculated the Laplace transform of e raised to power minus alpha t into u of t, and we calculated the Laplace transform of e raised to power minus alpha t into u of t, and the Laplace transform was equal to 1 over s plus a. So whenever we need to calculate the inverse Laplace of this 1 over s plus alpha, we'll directly write that the inverse Laplace of 1 over s plus alpha would be equal to e raised to power minus alpha t into u of t. Similarly, whenever we need to calculate the inverse Laplace of 1, we'll say that the inverse Laplace of f of s equal to 1 would be impulse function. So for inverse Laplace calculation, we need to remember these Laplace transform pairs, that if time domain function is Laplace of impulse of t, its s domain function would be, or its s domain transform would be f of s is equal to 1. So we need to remember these basic Laplace transform pairs. Uniqueness property. Uniqueness property states that if Laplace transform of f of t is equal to f of s, then inverse Laplace of f of s is, this is equal sign in parentheses. What does this equal sign in parentheses means? It means equal almost everywhere. Equal almost everywhere. So inverse Laplace transform of f of s is equal almost everywhere to f of t into u of t. What does it mean? When we calculated the Laplace transform of f of t and we represented the transform by f of s. Now we are taking the inverse Laplace transform of f of s, then it would be equal almost everywhere to f of t into u of t. What does it mean? It means the result of inverse Laplace transform is always a function f of t multiplied by u of t. What is the result of when a function is multiplied by u of t? We know that what is u of t? U of t is a unit step function which is sketched over here. U of t is equal to 1 for t greater than equal to 0 and is 0 otherwise. So when we multiply a function with this function, it means f of t into u of t would be existing for t greater than or equal to 0 only. Such a function is known as a causal function. Causal function. Causal function means exists for t greater than equal to 0 and is 0 for t less than 0. Whenever we multiply a function by unit step function, the result is always a causal function, and a causal function is a one having amplitude equal to 0 for t less than 0 and amplitude exists for t greater than equal to 0. It means when we calculate the Laplace transform, our function should be a causal function. If this function is not a causal function, it means after calculating the Laplace transform, when we go back, the result is going to be causal function. If the initial function was not causal, it means the result would not be the same. This is known as uniqueness property. This f of t for which we calculate the Laplace transform, this function must be a causal function for the uniqueness property to hold. Let's say an exponential function e raised to power minus alpha t, or let's say e raised to power minus 1t, e raised to power minus t. What is the sketch of this function? This function, like this is t is equal to minus infinity, this is t is equal to infinity, and the sketch for e raised to power minus alpha t is going to be something similar to this one. This is amplitude 1. For negative values of t, amplitude is higher, and for t greater than 0, amplitude is decreasing, and after 5 time constant, amplitude would be 0. This is the sketch of e raised to power minus alpha t when t is from minus infinity to plus infinity. What is the sketch of e raised to power minus alpha, e raised to power minus t into u of t? Because we have multiplied that function by u of t, it means now the sketch of e raised to power minus alpha t into u of t is going to be like this only. This is 1 amplitude. After 5 time constant, this amplitude is going to be 0. This is the sketch of e raised to power minus alpha t into u of t. If the original signal for which we calculated the Laplace transform is this signal e raised to power minus t into u of t, it means the original signal would be a causal signal for which we calculated Laplace transform, and from the Laplace transform f of s, when we convert back into the time domain signal, our result is going to be e raised to power minus t into u of t, and otherwise if we had calculated the Laplace transform of e raised to power minus t only, and then we calculated f of s, and based on this f of s, when we calculated back the time domain signal would be different from this one. So for Laplace transform, our signal, time domain signal, for which we calculate the Laplace transform that must be a causal signal or function in order for the uniqueness property to hold. Next are the properties of Laplace transform. First one is the linearity property. Linearity property is a combined name for additive property and multiplicative property. When we say that the Laplace transform is linear, it means additive property and the multiplicative property holds for the Laplace transform. Let's say we have two time domain functions, f1 of t and f2 of t. Laplace transform of f1 of t is represented by f1 of s, and similarly Laplace transform of f2 of t, let's say this is represented by f2 of s. Because Laplace transform is linear, therefore when we multiply our function, time domain function f1 of t by a constant k and calculate the Laplace transform, here f1 of t is multiplied by a constant k and then we calculated the Laplace transform, it means the Laplace transform must be equal to same multiplying factor k multiplied in s domain, k f1 of s. This is the multiplication property. Similarly, if f2 is multiplied by some other constant, let's say a, and then we calculated the Laplace transform, it means result would be a times f2 of s. And linearity property, since this is the combination of additive property and multiplicative property, if we take the Laplace transform of a f1 of t, where a is a constant, plus b f2 of t, then the result would be, because this is constant, constant would appear as it is over here, and we know that the Laplace transform of f1 of t is f1 of s, like this. Similarly, this is b constant appearing over here, and Laplace transform of f2 of t is represented by f2 of s. So this equation must be satisfied for the linearity property to hold. It means, let's say we need to calculate the Laplace transform of u of t plus Laplace transform of e raised to power minus alpha t u of t. We have already calculated the Laplace transform of both of these two functions. Laplace transform of u of t was equal to 1 over s. So 1 over s plus Laplace transform of e raised to power, here we do not need to use L. So Laplace transform of e raised to power minus alpha t into u of t, which we have already calculated, this thing was equal to 1 over s plus a. This is the use of linearity property. Next property of Laplace transform is integration property. Integration property I'll explain the result at the end. Before that, let's check what is integration property. Integration property means, let's say we have two functions. One is f1 of t and the second function is f2 of t. Both of these two functions are related in such a way that the second function is equal to the integration of first function. We have two functions, f1 of t and f2 of t. Second function is the integral of the first function. Here I have represented the integral of the first function as second function. Let's say we calculated the Laplace transform of the first function, and that is equal to f1 of s, right? How did we calculate the Laplace transform of the first function? Using the formula used for calculating the Laplace transform, integration from 0 minus to infinity f1 of t into e raised to power minus st dt. And let's say we calculated the Laplace transform of the first function and represented it by f1 of s. Now we can calculate the Laplace transform of the second function. How? By inserting f2 of t in this formula, and we can calculate our f2 of s. But then, since f1 and f2 are related in time domain, and how they are related? Integral of first function is equal to second function. We want to relate that how f1 of s and f2 of s would be related with each other, so that every time we do not need to calculate Laplace transform of two functions when they are related by integration of one function with the other. Every time we do not need to calculate Laplace transform of both of these two functions, rather we have a formula where we can calculate the Laplace transform of one function and we can relate the Laplace transform of the second function. So Laplace transform of f2 of t can be calculated using the formula used for Laplace transform calculation, which is integration of the function into e raised to power minus st over limit 0 minus to infinity. When we inserted f2 of t in terms of f1 of t, here this is the value for f2 of t which we inserted from this equation over here. E raised to power minus st into dt as it is. Now we can apply integration by parts formula, and integration by parts formula is represented by this sticky note over here. Integration of u into dv function is equal to uv minus v into du. So we can identify our u and v functions from here. U function is taken as this function. This is taken as u, whereas dv is taken as e raised to power minus st into dt. And based on this u and dv, we can take the derivative of this u and we can take the integral of this v so that we can calculate the values of required parameters. So derivative of u with respect to t would be equal to du over dt is equal to, because we have integral on the right hand side, when we take the derivative, integral would be cancelled out and result would be f1 of t only. Next, because we have dv over here, so we can integrate on both sides, and integrating on both sides result in v is equal to e raised to power minus st over s. So now we can calculate this f2 of s using the integration by parts formula, and we can substitute the values of u, v and v into du over here, and this is the value of u multiplied by v and this is the value of v multiplied by du. So because the limits of the integration over here are from 0 minus to infinity, therefore we need to substitute the limits from 0 minus to infinity. So this is the limit substituted for this uv factor. Limit is from 0 minus to infinity, and similarly for the integration part, the limit is from 0 minus to infinity. Okay, now if we focus on substituting limits, when we substitute the limit in this factor, upper limit substitution, we substitute the value for t, therefore this is going to be minus e raised to power minus infinity. E raised to power minus infinity is always 0. So this, when this factor becomes equal to 0, multiplied by anything would be equal to 0. So substituting the upper limit results in 0. 0, basically this factor reduces to 0 when we substitute the upper limit as infinity, minus the lower limit. For lower limit, this factor is going to be e raised to power minus st, which is e raised to power 0. This is going to be 1. So we can make it plus 1 over s. What about this one? Because we substitute t equal to 0. When we substitute this t equal to 0, it means we are integrating function f1 of t over a point from 0 to 0. Integrating a function f1 of tau over a limit or over a range 0 to 0 results in 0 value. So it means basically this complete factor, when we substitute the limit, results in 0 and minus, this is 0 minus to infinity as it is. We can take this minus 1 over s outside the integral. So rest of the thing is f1 of t into e raised to power minus st dt. And if we focus on this part, this minus can also be taken outside, therefore it would convert this minus into plus. And if we focus on this part, this is the same formula which we used to calculate Laplace transform of f1 of t, and that was equal to f1 of s. So this thing results in, this is 0 plus 0 equal to 0, and the rest of the thing is this vector, and we know that this vector can be written as f1 of s. Therefore, we say that the Laplace transform of second function is equal to Laplace transform of first function divided by s. So it means to say, whenever two functions are related in such a way that the integral of one function is equal to the second function, then we only need to calculate the Laplace transform of the first function, and the Laplace transform of the second function can be calculated using the Laplace transform of the first function divided by s. In case of inductor and capacitor, voltage and current are usually related by either integral or derivative. Therefore, when the equation involves integral, we can directly apply the integration property of Laplace transform, and we can calculate the Laplace transform of any required parameter. Okay, so the final conclusion of integration property is, it states that the time domain integration of a waveform f of t can be accomplished in the s domain by algebraic process of dividing its transform f of s by s. Let's calculate the Laplace transform of this function, which is a ramp function, and ramp is equal to t into u of t. We can calculate the Laplace transform of t into u of t. Ramp function r of t, we can also write it as t. This is equal to integration of unit step function. Integration of unit step function is going to be, because u of t is equal to 1, so when we integrate 1, it results in tau, and that would be equal to upper limit substituted as t, lower limit substituted as 0, so t minus 0 would be equal to t. So integral of a unit step function is basically a ramp function r of t, which is equal to t. So it means we can say that this ramp function is the integral of the unit step function, right? And we know the Laplace transform of unit step function is equal to 1 over s. Using the integration property of Laplace transform, because ramp function is the integral of unit step function, and based on the integration property, we know that Laplace transform of ramp multiplied by u of t is making causal, is going to be, this is f of s divided by s. So this is going to be 1 over s square. Laplace transform using the integration property we have calculated as 1 over s square. Obviously, there is an alternate method that you can calculate the Laplace transform of this function using the standard procedure for calculating Laplace transform, which is f of s, let's say f of s is equal to integration from 0 minus to infinity of t into u of t into e raised to power minus st dt, and it would be integration limits from 0 to infinity for t into e raised to power minus st dt. I have replaced u of t by 1. Again, we need to apply the integration by parts formula, because we have two functions over here, one is t and the second one is e raised to power minus st. So you can apply the integration by parts formula yourself, and you need to calculate, or you need to solve this integral, and the result would be 1 over s square. Second numerical related to integration properties, let's say we have two functions. First one is v1 of t, which is equal to va into e raised to power minus alpha t u of t volts. This is a voltage function, so the units are volts. We have a second function which is equal to integration from 0 to t va into e raised to power minus alpha x dx. E raised to power minus alpha x dx is nothing but this t replaced by x, so we have changed variable basically. It means we can say that v2 of t is the integral of v1 of t basically. So it means let's calculate Laplace transform of v1 of t only, and after calculating Laplace transform of v1 of t, we will directly calculate Laplace transform of v2 of t using the integration property. So Laplace transform of v1 of t, that would be equal to integration from 0 minus to infinity of va is constant, into e raised to power minus alpha t, e raised to power minus alpha t into u of t into e raised to power minus st dt. So the Laplace transform of v1 of t would be equal to integration from, instead of writing 0 minus, I am writing 0 because u of t would be 1 for 0 to infinity. So va, this is constant, it can be taken out of integration. So e raised to power minus t can be taken common. So this is going to be alpha plus s. U of t is replaced by 1 into dt. So va taken out of integration, and the rest of the thing is integration of e raised to power minus t into alpha plus s. We can multiply and divide by minus alpha plus s minus alpha plus s into dt. So va divided by minus alpha plus s, the 1 in the denominator can be taken out of integral sign, and the rest of the thing would be e raised to power integration of e raised to power minus t into alpha plus s. When we have derivative of the power available, it is going to be e raised to power minus t into alpha plus s. Same. Integration limits are from 0 to infinity. When we substitute the upper limit minus alpha plus s, when we substitute the upper limit e raised to power minus infinity, this is going to be 0 minus, when we substitute the lower limit, it is going to be e raised to power minus 0 or e raised to power 0, which is 1. Or f of s is equal to, let's say f1 of s is equal to 1 over alpha plus s. Because we know that the second function v2 of t is the integral of the first function. Therefore, Laplace transform of the second function f2 of s would be f1 of s divided by s. So this is going to be 1 over s into alpha plus s based on the integration property. Next is differentiation property. And the differentiation property means, let's say we have two functions f1 of t and f2 of t. And the second function f2 of t is the derivative of the first function f1 of t. It means instead of step by step calculating the Laplace transform of both of the two functions, we will calculate the Laplace transform of the first function only, and then based on the differentiation property, we will relate the Laplace transform of f2 of s with the Laplace transform of f1 of s. Let's say we have calculated the Laplace transform of f1 of s, that is this value. How should we calculate Laplace transform of f2 of t? This is the step-by-step formula or procedure to calculate Laplace transform of second function f2 of t. So when we substitute this equation of f2 of t over here, because f2 of t is the derivative of f1 of t, so we end up with this equation. Again, we need to apply the integration by parts formula, and we'll assume that our u function is e raised to power minus st only, and the dv function is derivative of f1 of t multiplied by dt. So this dt can be cancelled by this dt. When we take integral, this is going to be v is equal to f1 of t, and from this u, when we take the derivative on both sides, we end up calculating du, which would be equal to minus s into e raised to power minus st multiplied by this dt. Okay, then we substitute the values of u, v and v into du in the integration by parts formula, which is this equation. And based on this equation, from this factor, when we substitute the upper limit, it reduces into f1 of infinity into e raised to power minus infinity, and we know that e raised to power minus infinity is equal to 0. Therefore, substituting the upper limit results in 0, means this factor reduces to 0. What about the lower limit? When we substitute the lower limit, this one reduces to f1 of 0 minus into e raised to power 0 minus or e raised to power 0. E raised to power 0, we know that this is 1. So this thing basically reduces to minus f1 of 0 minus. So minus f1 of 0 minus as it is, and this factor, because this s is constant, so it can be taken out of integration, and when this negative multiplied by this negative, it reduces into plus s. And the rest of the thing, which is this part, integration from 0 minus to infinity f1 of t into e raised to power minus st dt. This is the standard formula for calculating Laplace transform of f1 of t, which is this equation basically. So we know that this is equal to f1 of s. So we got this result: Laplace transform f2 of s is equal to s f1 of s, means the Laplace transform of the first function multiplied by s minus f1 of 0 minus. What is this f1 of 0 minus? This is basically the time domain function evaluated at 0 minus. Time domain function, this f1 of t evaluated at 0 minus. So this is the differentiation property, that if we have two functions and one function is the derivative of the second function, it means the Laplace transform of function would be equal to the Laplace transform of the original function multiplied by s minus the function evaluated at 0 minus. So the properties of the Laplace transform are really important, and you must remember how to calculate the Laplace transform of one function based on the Laplace transform of the other function when the second function is related with the differential or the integral of the first function. Practice problem related to the derivative property is calculate Laplace transform of the two functions. One is sine of beta t into u of t, and the second one is cos of beta t into u of t. We know that we can calculate the Laplace transform of f1 of t using the standard formula used to calculate the Laplace transform, which is integration from 0 minus to infinity for the function f1 of t into e raised to power minus st dt, right? So for this f1 of t, we can insert sine of beta t into u of t, or alternatively, we know that using Euler's identity, this sine of beta t into u of t can be written as e raised to power beta t e raised to power j beta t minus e raised to power minus j beta t divided by 2j So if I put f1 of t equal to sine of beta t into u of t over here, it means I need to use the integration by parts formula, and it would be much easier if I use this Euler's identity to calculate the Laplace transform of sine of beta t, because we know that our f1 of t is now written as e raised to power j beta t over 2j into u of t minus e raised to power minus j beta t u of t divided by 2j. So Laplace transform of f1 of t would be equal to Laplace transform of the right hand side, which is e raised to power j beta t u of t divided by 2j minus e raised to power minus j beta t over 2j into u of t. Using the linearity property, we can take the Laplace transform of the right hand side, Laplace transform of this thing minus the Laplace transform of this thing. So it can be written as Laplace transform of e raised to power j beta t into u of t divided by 2j. 2j is constant over here, minus Laplace transform of e raised to power minus j beta t over 2j into u of t. So here is 2j is constant. Similarly, 2j is constant over here. And the rest of the thing is exponential function multiplied by a unit step function. Exponential function multiplied by a unit step function. And unit step function does nothing except converting the function into a causal function. So we have already calculated Laplace transform of a unit step function. We have already calculated the Laplace transform of the unit step function, and we know that the Laplace transform of unit step function 1 over 2j as it is, Laplace transform of e raised to power j beta t, this is equal to 1 over s minus j beta minus 1 over 2j, which is the constant, multiplied by the Laplace transform of e raised to power minus j beta t into u of t, and this is equal to 1 over s plus j beta, because we already know how to calculate the Laplace transform of an exponential function. So 1 over 2j can be taken common, and the rest of the thing would be 1 over s minus j beta into 1 over s plus j beta, and this is going to be 1 over, this is a minus b multiplied by a minus a minus b. So 1 over s minus j beta minus 1 over s plus j beta. S plus j beta, and this thing would be, we can take LCM, and that would be, denominator would become a square minus b square, so plus beta square, and numerator would become s plus j beta minus s plus j beta. So this is 1 over 2j into s cancelled out, this is 2j beta, 2j would be cancelled here, and denominator would be s square plus beta square. So it would reduce to beta over s square plus beta square. So the Laplace transform of f1 of t, which is sine of beta t into u of t, if I represent it by f1 of s, because the original function was represented by f1 of t, this is equal to beta over s square plus beta square. A very, very important result which needs to be remembered. that the Laplace transform of sine of beta t is beta over s square plus beta square. Derivative of f1 of t. What is the derivative of f1 of t? Derivative of sine of beta t into u of t. Derivative of sine of beta t is cos of beta t into beta. So we can write f2 as 1 over beta multiplied by derivative of f1 of t. U of t is doing nothing but just making it causal. So derivative of f1 of t. So we can say that the Laplace transform of f2 of t would be equal to Laplace transform of right hand side, which is 1 over beta is constant, it would stay as it is. So 1 over beta multiplied by Laplace transform of derivative of f1 of t. Laplace transform of the derivative of f1 of t. Using the derivative property of Laplace transform, this is going to be s f1 of s minus the function evaluated at 0. Which function? Sine of beta t. So sine of beta t evaluated at 0 would be sine 0 would be 0. So this one. So f2 of s can be now written as this beta in denominator would be cancelled by this beta of in the numerator of f1 of s. So result would be s over s square plus beta square. This is the Laplace transform of cos of beta t into u of t. Very, very important result. This result needs to be remembered that the Laplace transform of sine of beta t is beta over s square plus beta square, whereas the Laplace transform of cos of beta t into u of t is s over s square plus beta square. The last property is translation property, but this property exists in two different domains, time domain and the frequency domain. So S domain translation property. What is the meaning of translation over here? The simple meaning of translation over here is shifting in S domain. S domain would be shifted. Let's say we have 1 over S, and shifting this S means we need to add or subtract something from this S. So 1 over S plus A, this is known as shifting in S domain. So S domain translation property states that if the Laplace transform of f of t is equal to f of s, let's say we have already calculated or we already know the Laplace transform of a function and represent it by f of s, then the Laplace transform of that function multiplied by an exponential function would result in the Laplace transform of this function shifted by the amount a. Sign is opposite. We have e raised to power minus at over here, and the shifting is represented by f of s plus a. What does it mean? It means that the multiplication of a function in time domain by an exponential function results in the shifting of the s domain function. This is the same property which I discussed in the start of the lecture, that we calculated Laplace transform of u of t, and that was equal to 1 over s. And when we calculated Laplace transform of e raised to power minus at into u of t, that was equal to 1 over s plus a. Laplace transform of this function we calculated, and we know that this is equal to 1 over s. What is this function? This is the product of u of t by an exponential function. Whenever we multiply a function, time domain function, by an exponential function in time domain, the result is shifting of the s domain function by the opposite sign of this amount, which is 1 over time constant. So maybe you do not need to go into the details of the time constant, just whatever the factor appears over here, shifting would be of the same value but with opposite sign in S domain. So this is very simple. We have inserted the function over here as f of t is equal to e raised to power minus n at, and we got the result which was f of s plus a over here. Why? Because this is f of t over here and we got e raised to power minus a over s plus t over here. So when we multiply and divide by minus of a plus s, we end up with f of s plus a result. So here we have few examples related to the time domain shifting property. This is Laplace transform of t into e raised to power minus at into u of t. We already calculated Laplace transform of t into u of t, which was what? 1 over s square. Because this thing was 1 over s square, so when we multiplied it by an exponential function in time domain, result is s shifted by the same amount with a negative sign, with an opposite sign. So 1 over s square, which was the Laplace of t into u of t, it converted into 1 over s plus a square because we multiplied the time domain function by e raised to power minus at. Similarly, we just calculated Laplace transform of cos of beta t into u of t, which was what? Laplace transform of cos of into u of t was equal to s over s square plus beta square, right? So when we multiply this function by e raised to power minus alpha t in time domain, s, every s shifted by the same amount. So this s converted into s plus alpha over here, and this s square converted into s plus alpha whole square over here. So this is the Laplace transform of e raised to power minus alpha t into sine of beta t into u of t. We know that the Laplace transform of sine of beta t is beta over s square plus beta square. So the s shifted by s plus alpha square, alpha. Next is time domain translation property. It means shifting in time domain basically. Let's say we need to calculate the Laplace transform of f of t minus a into u of t minus a over here. When we step by step calculate the Laplace transform of this function, because this is f of t minus a into u of t minus a over here. So u of t minus a means the value would be 1 starting from t is equal to a onward. T is equal to a up to infinity, value would be 1, and value would be equal to 0 from minus infinity to a minus, just before a. So we have replaced this u of t minus a by 1 and we converted the lower limit to a. Why a? Because we are replacing this by 1 and this value would be 1 starting from a up to infinity. So lower limit is a, upper limit is infinity. U of t minus a is replaced by 1 and the rest of the thing is f of t minus a as it is, and the rest of the things are all same. So we can change variable over here. Let's say t minus a is replaced by a new variable tau. We can rearrange this equation and write t as tau plus a. And if we take the derivative of this equation, it means dt would be equal to d tau. What next? It means we can write this equation in the form of our new variables now. So f of t minus a would be written as f of tau and e raised to power minus st minus s as it is, and we know that t can be written as tau plus a, therefore e raised to power minus st can be written as e raised to power minus s tau and e raised to power minus s. We have separated the power basically, and dt is equal to d tau, therefore this dt is replaced by this d tau over here. Secondly, the limits of integration, because here we have dt as the parameter of integration and here we have d tau, therefore the limits in this equation were in the form of t, that the t was varying from a is equal t was varying from a to infinity, whereas now we need to replace the limits in terms of tau. When t is equal to a, if I put limits in this equation, when t is equal to a, it means what about tau? Tau would be equal to 0. to satisfy the equation. It means lower limit would be, in terms of tau, it would be 0. And when t is equal to infinity, it means tau would be equal to infinity as well, so the upper limit stays the same. So here the limits are in terms of tau, whereas in this equation limits are in the form of t. Right. Then e raised to power minus s is constant over here. It can be taken out of integration, and the rest of the thing is f of tau into e raised to power minus s tau d tau integration limits from 0 to infinity. And we know that this is similar with the formula of calculating Laplace transform of a function. So we can replace it by f of s. It means the Laplace transform of this function shifted in time domain to f of s. So the result is multiplication e raised to power minus as, multiplication of the frequency domain function by an exponential function by the sign, because and t is replaced as a over here. Usually f of t, because the result of for example, which is capital T. T is shifted. We know that the of t minus tau as domain function of u of e raised transform in translation property. The knowledge transform that the frequency domain function